Soyuz is a series of spacecraft designed from the Soviet space program by the Korolyov Design Bureau in the 1960s that remains in service today. The Soyuz succeeded the Voskhod spacecraft and was originally built as part of the Soviet Manned Lunar program. The Soyuz spacecraft is launched on a Soyuz rocket, the most frequently used and most reliable launch vehicle in the world to date. The Soyuz rocket design is based on the Vostok launcher, which in turn was based on the 8K-74 or R-7A Semyorka, a Soviet intercontinental ballistic missile. All Soyuz spacecraft are launched from the Baikonur Cosmodrome in Kazakhstan. History: the first Soyuz flight was unmanned and started on November 28, 1966. The first Soyuz mission with a crew, Soyuz 1, launched on the 23rd of April 1967 but ended with a crash due to a parachute failure, killing cosmonaut Vladimir Komarov. The following flight was unmanned. Soyuz 3, launched on October 26, 1968, became the program's first successful manned mission. The only other flight to suffer a fatal accident, Soyuz 11, killed its crew of 3 when the cabin depressurized prematurely just before re-entry. These were the only humans to date to have died above the Kármán line. Despite these early incidents, Soyuz is widely considered the world's safest, most cost-effective human spaceflight vehicle, established by its unparalleled length of operational history. Soyuz spacecraft were used to carry cosmonauts to and from Salyut and later Mir Soviet space stations, and are now used for transport to and from the International Space Station. At least one Soyuz spacecraft is docked to ISS at all times for use as an escape craft in the event of an emergency. The spacecraft is intended to be replaced by the 6-person Federation spacecraft. Design: a Soyuz spacecraft consists of 3 parts: a spheroid orbital module, which provides accommodation for the crew during the mission; a small aerodynamic re-entry module, which returns the crew to Earth; a cylindrical service module with solar panels attached, which contains the instruments and engines. The orbital and service modules are single-use and are destroyed upon re-entry in the atmosphere. The orbital and re-entry portions are habitable living space. Soyuz can carry up to 3 crew members and provide life support for about 30 person days. The life support system provides a nitrogen-oxygen atmosphere at sea level partial pressures. The atmosphere is regenerated through CO2 cylinders, which absorb most of the CO2 and water produced by the crew and regenerates the oxygen, and lithium hydroxide cylinders which absorb leftover CO2. The vehicle is protected during launch by a payload fairing, which is jettisoned after passing through the atmosphere. It has an automatic docking system. The ship can be operated automatically, or by a pilot independently of ground control. Orbital module: the forepart of the spacecraft is the orbital module, also known as habitation section. It houses all the equipment that will not be needed for re-entry, such as experiments, cameras, or cargo. The module also contains a toilet, docking avionics and communications gear. Internal volume is 6 cubic meters, living space 5 cubic meters. On the latest Soyuz versions, a small window was introduced providing the crew with a forward view. A hatch between it and the descent module can be closed so as to isolate it to act as an airlock if needed. Crew members exiting through its side port. On the launch pad, the crew enter the spacecraft through this port. This separation also lets the orbital module be customized to the mission with less risk to the life-critical descent module. The convention of orientation in a micro-G environment differs from that of the descent module. as crew members stand or sit with their heads to the docking port. Also, the rescue of the crew whilst on the launch pad with SHASH system is complicated because of the orbital module. Separation of the orbital module is critical for a safe landing. Without separation of the orbital module, it is not possible for the crew to survive landing in the descent module. In view of this, the orbital module was separated before the ignition of the return engine until the late 1980s. This guaranteed that the descent module and orbital module would be separated before the descent module was placed in a re-entry trajectory. However, after the problematic landing of Soyuz trademark 5 in September 1988, this procedure was changed and the orbital module is now separated after the return maneuver. This change was made as the trademark 5 crew could not deorbit for 24 hours after they jettisoned their orbital module, which contained the sanitation facilities and the docking collar needed to attach a mirror. The risk of not being able to separate the orbital module is effectively judged to be less than the risk of needing the facilities in it. Following a failed deorbit, re-entry capsule. The re-entry capsule, Spassky Mir Parrot, also known as descent module, is used for launch and the journey back to Earth. Half of the re-entry capsule is covered by a heat-resistant covering to protect it during re-entry. This half faces the Earth during re-entry. It is slowed initially by the atmosphere, then by a braking parachute, followed by the main parachute which slows the craft for landing. At 1 meter above the ground, solid fuel braking engines mounted behind the heat shield are fired to give a soft landing. One of the design requirements for the re-entry capsule was for it to have the highest possible volumetric efficiency. The best shape for this is a sphere, as the pioneering Vostok spacecraft's descent module used, but such a shape can provide no lift, which results in a purely ballistic re-entry. Ballistic re-entries are hard on the occupants due to high deceleration and cannot be steered beyond their initial deorbit burn. That is why it was decided to go with the headlight shape that the Soyuz uses, a hemispherical forward area joined by a barely angled conical section to a classic spherical section heat shield. This shape allows a small amount of lift to be generated due to the unequal weight distribution. The nickname was thought up at a time when nearly every headlight was circular. Small dimensions of the re-entry capsule led to it having only 2 man-crews after the death of the Soyuz 11 crew. The later Soyuz T spacecraft solved this issue. Internal volume of Soyuz R is 4 cubic meters. 2.5 cubic meters is usable for crew. Service module. At the back of the vehicle is the service module, Preborno Aggregatny Otsek. It has a pressurized container shaped like a bulging can that contains systems for temperature control, electric power supply, long-range radio communications, radio telemetry, and instruments for orientation and control. A non-pressurized part of the service module contains the main engine and a liquid-fueled propulsion system for maneuvering in orbit and initiating the descent back to Earth. The ship also has a system of low-thrust engines for orientation attached to the intermediate compartment. Outside the service module are the sensors for the orientation system and the solar array, which is oriented towards the Sun by rotating the ship. An incomplete separation between the service and re-entry modules led to emergency situations during Soyuz 5, Soyuz TMA-10 and Soyuz TMA-11, which led to an incorrect re-entry orientation. The failure of several explosive bolts did not cut the connection between the service re-entry modules on the latter 2 flights. Re-entry procedure. The Soyuz uses a method similar to the Apollo to deorbit itself. The spacecraft is turned engine forward and the main engine is fired for deorbiting fully 180 degrees ahead of its planned landing site. This requires the least propellant for re-entry. The spacecraft travels on an elliptical Hohmann orbit to a point where it will be low enough in the atmosphere to re-enter. Early Soyuz spacecraft would then have the service and orbital modules detached simultaneously from the re-entry module, as they are connected by tubing and electrical cables to the re-entry module. This would aid in the separation and avoid having the descent module alter its orientation. Later Soyuz spacecraft detach the orbital module before firing the main engine, which saved propellant. Since the Soyuz trademark 5 landing issue, the orbital module is once again detached only after the re-enter firing, which led to emergency situations of Soyuz TMA-10 and TMA-11. The orbital module cannot remain in orbit as an addition to a space station, as the airlock hatch between the orbital and re-entry modules is a part of re-entry module, and the orbital module therefore depressurizes after separation. Re-entry firing is usually done on the dawn side of the Earth, so that the spacecraft can be seen by recovery helicopters as it descends in the evening twilight, illuminated by the sun when it is above the shadow of the Earth. The Soyuz craft is designed to come down on land, usually somewhere in the deserts of Kazakhstan in Central Asia. This is in contrast to early U.S. manned missions which splashed down in the ocean. Spacecraft systems. Thermal control system, Systema obezpieczenia teplowego reżimu SOTR. Life support system, Kompleks R-7A obezpieczenia żyznadejatelności KSOZH. Power supply system, Systema elektropitania, September. Communication and tracking systems, Razvet radio communications system, onboard measurement system, KVAN-TV spacecraft control, ClearStem television system, orbit radio tracking. Onboard complex control system, Systema upravlenia bortowym kompleksem SUBK. Combined propulsion system, Kompleksna uwagatelna ustanowka KDU. CHAIKA3 motion control system, optical visual devices, VSK4 night vision device, docking light, pilot's sight, laser rangefinder. Ker's rendezvous system, docking system, Systema Stykovki IV neutrinego pericoda SSVP. Teleoperator control mode, teleoperatorny režim upravlenia Toru. Entry actuators system, Systema исполнительных органов спуска COS. Landing aids kit, Kompleks REDSTV prizemlenia KSP. Portable survival kit, Nozomi avriony zapis, NAS, containing a TP-82 or other pistol. Soyuz launch escape system, Systema avianego spazenia SHASH. Variants. The Soyuz spacecraft has been the subject of continuous evolution since the early 1960s. Thus, several different versions, proposals and projects exist. Specifications. Soyuz 7K. Korolyov initially promoted the Soyuz ABV circumlunar complex concept, in which a two-man craft Soyuz 7K would rendezvous with other components in Earth orbit to assemble a lunar excursion vehicle, the components being delivered by the proven R-7 rocket. First generation. The manned Soyuz spacecraft can be classified into design generations. Soyuz 1 through Soyuz 11 were first-generation vehicles, carrying a crew of up to 3 without spacesuits and distinguished from those following by the bent solar panels and the use of the IGLA, automatic docking navigation system, which required special radar antennas. This first generation encompassed replaced the original Soyuz 7KOK and the Soyuz 7KOKS for docking with the Salyut 1 space station. The probe and drogue docking system permitted internal transfer of cosmonauts from the Soyuz to the station. The Soyuz 7KL-1 was designed to launch a crew from the Earth to circle the Moon, and was the primary hope for a Soviet circumlunar flight. It had several test flights in the Zond program from 1967 to 1970, which produced multiple failures in the 7KL-1's re-entry systems. The remaining 7KL-1s were scrapped. The Soyuz 7KL-3 was designed and developed in parallel to the Soyuz 7KL-1, but was also scrapped. Soyuz 1 was plagued with technical issues, and cosmonaut Vladimir Komarov was killed when the spacecraft crashed during its return to Earth. This was the first in-flight fatality in the history of spaceflight. The next manned version of the Soyuz was the Soyuz 7KOKS. It was designed for space station flights and had a docking port that allowed internal transfer between spacecraft. The Soyuz 7KOKS had two manned flights, both in 1971. Soyuz 11, the second flight, depressurized upon re-entry, killing its three-man crew. Second generation. The second generation, called Soyuz Feria Soyuz 7KT, comprised Soyuz 12 through Soyuz 40. It was developed out of the military Soyuz concepts studied in previous years and was capable of carrying two cosmonauts with Sokol spacesuits. Several models were planned, but none actually flew in space. These versions were named Soyuz P, Soyuz PPK, Soyuz R, Soyuz 7KV, and Soyuz OIS. The Soyuz 7KT-A9 version was used for the flights to the military Almaz space station. Soyuz 7K trademark was the spacecraft used in the Apollo-Soyuz test project in 1975, which saw the first and only docking of a Soyuz spacecraft with an Apollo command service module. It was also flown in 1976 for the Earth Science Mission, Soyuz 22. Soyuz 7K trademark served as a technological bridge to the third generation. The third generation Soyuz T spacecraft featured solar panels allowing longer missions, a revised IGLA rendezvous system and new translation attitude thruster system on the service module. It could carry a crew of 3, now wearing spacesuits. Fourth generation Soyuz trademark. The Soyuz trademark crew transports were fourth generation Soyuz spacecraft, and were used from 1986 to 2003 for ferry flights to Mir in the International Space Station. Soyuz TMA features several changes to accommodate requirements requested by NASA in order to service the International Space Station, including more latitude in the height and weight of the crew and improved parachute systems. It is also the first expendable vehicle to feature glass cockpit technology. Soyuz TMA looks identical to a Soyuz trademark spacecraft on the outside, but interior differences allow it to accommodate taller occupants with new adjustable crew couch. Soyuz TMAM. The Soyuz TMAM was an upgrade of the baseline Soyuz TMA, using a new computer, digital interior displays, updated docking equipment, and the vehicle's total mass was reduced by 70 kilograms. The new version debuted on the 7th of October 2010 with the launch of TMA-01M, carrying the ISS Expedition 25 crew. The Soyuz TMA-08M mission set a new record for the fastest manned docking with a space station, event utilized the new 6-hour fast rendezvous instead of the previous Soyuz launches, which had, since 1986, taken 2 days. Soyuz MS is the final planned upgrade of the Soyuz spacecraft. Its maiden flight was in July 2016 with mission MS-01. Major changes include more efficient solar panels, modified docking and attitude control engine positions for redundancy during docking and orbit burns, new Kurzner approach and docking system which weighs half as much and consumes a third of the power of previous system, new TSVM-101 computer, about 1/8 the weight and much smaller than the previous Argon-16 computer, unified digital command telemetry system to relay telemetry via satellite, and control spacecraft when out of sight of ground stations, also provides the crew with position data when out of ground tracking range. GLONASS GPS and COSPAR-SARSAT satellite systems for more accurate location during search rescue operations after landing. Related craft. The unmanned Progress spacecraft were derived from Soyuz and are used for servicing space stations, while not being direct derivatives of Soyuz. The Chinese Shenzhou spacecraft and the Indian orbital vehicle follow the same general layout as that pioneered by Soyuz. Operators: Soviet Union, 1966 to 1991. Russian Federation, 1992 to present. Missions. See List of Soviet manned space missions and List of Russian manned space missions as well as the Zond program. Image gallery.